Hey folks, here in section 7.3, we're going to look at logarithmic and exponential functions with other bases. So these are bases other than e. All right, so here's a little recap. We know the natural log of e to the x equals x. The natural log of e is equal to 1. And we know e to the natural log x equals x. So that means, for example, that e to the natural log 2 equals 2. E to the natural log 3 equals 3. And e to the natural log b is equal to b. It's that latter one, e to the natural log b equals b. That means we can take the exponential expression b to the x, and it can be rewritten as b to the x equals e to the natural log b, that quantity to the x power. And that's because that b in b to the x, b is equal to e to the natural log b. And then we can use a property of exponents, the e raised to the natural log b, that whole expression raised to the x power. We can multiply the x times the natural log b to get e to the natural log b times x. So the exponent for e is natural log b in parentheses times x. So we can rewrite b to the x as e to the natural log b x. And that gives us the following definition. So if b is greater than 0, not equal to 1, and x is any real number, then the exponential function f of x equals b to the x is defined to be f of x equals b to the x equals e to the natural log b of x. And you can see where I'm going to go with this. We know how to differentiate exponential functions where the base is e. We just learned that in the previous section. So when the base is different, it's a generic b. We see how we're going to rewrite it so we can then get the derivative. But before we get to that, before we get there, we have some more stuff we have to review. So for the function f of x equals b to the x, and again, b is positive, not equal to 1, the inverse function is g of x equals log base b of x. And because they are inverses of each other, we know when we do the composition, f of g of x, it has to simplify to x. And when we do the composition g of f of x, it has to simplify to x. That gives us the following facts. B to the log base b of x equals x, and log base b of b to the x equals x. In college algebra, you should have learned something called the change of base formula. So I'm just going to review that real quick. That when you have log base b of x, you can rewrite that as the natural log x over the natural log b. Or if you prefer, that's 1 over the natural log b times natural log x. So folks, we now have all the weapons to figure out what the derivative of b to the x is and what the derivative of log base b of x happens to be. Respectively, we're going to rewrite b to the x. We're going to rewrite that as e to the natural log b x. And log base b of x, we're going to rewrite as 1 over the natural log b times natural log x. And, so let me go through this, step by step. So when you differentiate b to the x, we're going to rewrite b as e to the natural log bx. We know how to compute the derivative of e to the natural log bx. It's e to the natural log bx times, remember the chain rule, the derivative of the exponent. Well, the derivative of the exponent, keep in mind, natural log b is just a constant, so the derivative of the exponent is just natural log b. And then we do a little bit of rewriting. We have natural log b, and this e to the natural log b, well, that's just b, which gives us, b to the x. So the derivative of b to the x is natural log b times b to the x, or if you prefer, you could write it as b to the x times natural log b. the derivative with respect to x of log base b of x. Well, we take log base b of x and we rewrite it using the change of base formula as 1 over natural log b times natural log x. And we know what the derivative of ln x is. Remember, this is just a constant. So the derivative would be this constant times the derivative of ln x, which is 1 over x, and multiply those two fractions together, and we get this. So the derivative with respect to x of log base b of x is 1 over natural log b times x. So really that's justification, motivation for the following theorem. And in this theorem, b is positive, not equal to 1, and u is some differentiable function of x. So part 1 says, well, we just derived this up here. The derivative of b to the x is b to the x times natural log b. Now, if u is a differentiable function, when we differentiate with respect to x, b to the u is a differentiable function of x, we get the derivative to be b to the u times natural log b times du dx. That's the chain rule. It's just saying the derivative of the exponent. Likewise, we just explained up above that the derivative of log base b of x is 1 over natural log b times x. And then number 4 here, again, remember u is a differentiable function of x. So the derivative starts off 1 over the natural log of b times u times du dx, the derivative of what this is. It's the chain rule part. So let's just practice these a little bit. We have 4 parts here. You know the drill. Get these written in the notes. We're going to head off to the chalkboard and work through them. All right, folks, let's look at how we can differentiate the following. Part A was f of x equals 3 to the x. So the derivative is just 3 to the x times the natural log 3. That's it. Or, you know, some of you prefer to write it as natural log 3 in parentheses times 3 to the x. I mean, it's the same thing, but, you know, that's it. Part B, we're going to have to use the product rule. So part B, see, the derivative is the derivative of the first function, which is 1, times the second function, plus the first function times, now the derivative of the second function is 4x natural log 4. And I'm just going to leave it like that. Part C. Part C was actually f of x equals, I left off the f of x, so let me put that up here. F of x equals log base 5 of 2x. And so the derivative for it is 1 over the natural log of 5 times a 1 over 2x, and then don't forget the chain rule, times 2. The derivative of 2x is 2. And, you know, we could rewrite that because the 2's would cancel out. So we could rewrite it as 1 over the natural log of 5 times x. And then there was a part D. So bear with me as I erase the board and get part D up here. And part D should look kind of familiar. It was the last example we did in section 7.2. It was an example of logarithmic differentiation. And I put this here because, you know, I'm going to show you an alternative way to do it. And that's we can rewrite the x sine x as, let me write that down. We can rewrite x sine x as e to the ln x to the sine x. Because e to the natural log x is the same thing as x. And then we can get the derivative because we know the derivative. Well, we know the derivative of e to the ln x sine x is e to the ln x sine x times, now the chain rule, you have to do the derivative of the exponent. So the derivative of the exponent, well, the derivative of the exponent is going to require the product rule, so I'm going to put down a square bracket. So the derivative of ln x is 1 over x times sine x plus ln x, and then the derivative of sine is cosine x. And then, again, the e to the natural log x, you can rewrite that as x. So you'd have x to the sine x times, and I would write that as sine x over x plus ln x cosine x. And that should be the same result that we had on the last example in section 7.2. So I just thought I would show you this as an alternative way to the logarithmic differentiation. But I do like the logarithmic differentiation. We're going to see it's going to pop up a couple of more times throughout calculus. So that's it for this example. Let's go back to the slides. I'm sure I'm going to do a couple of examples where we integrate, and then that's going to be it for this section. Truth of the matter is, in the exponential and logarithmic world, by and large, we deal with exponential functions that have a base of e and logarithmic functions that also have a base of e, natural logs. So this is kind of a short, sweet section. But let's head back to the slides and see what's next. All right, now that we did a brief little practice with derivatives, it's time to look at, integrating. So the antiderivative of b to the x dx, that antiderivative is 1 over natural log b times b to the x. And, well, let's do some practice. So in this example, we're going to integrate. I have 2 of them. You know the drill. Write them down. Get them in your notes because I'm heading off to the chalkboard to work through them. All right, folks, part A, integrate 3 to the x. Quite simply, it's one step. It's 1 over the natural log 3 times 3 to the x plus c. That's it. Part B. Well, part B, we have to do a u sub. We have to let u equal x squared. du is a 2x dx. So when we substitute in, we get a 5 to the u. Now we still need to take care of the x dx. 1/2 du is x dx. So we substitute in the 1/2 du, rip the 1/2 out front. Antiderivative of this, of 5 to the u, is just 1 over the natural log 5 times 5 to the u plus c. And resubstitute. And that is it. So, that's it for this section. It's a very short, sweet section. So at this time, you could definitely do the exercises I've assigned in section 7.3. So go do the section 7.3 exercises, and thanks for watching.